Imagine a world where the sky is no longer the limit, but a new frontier for urban commuting. How close are we to this future? Closer than you might think. The revolution of urban commuting is on the horizon, and it's taking us skyward. Welcome to the age of urban air mobility. Urban air mobility, or UAM, is not just a concept from science fiction. It's an emerging part of the transportation ecosystem that uses the skies to alleviate congestion on the ground. Picture this: air taxis, drones, and other aerial vehicles zipping through the skies, transporting people and goods with speed and efficiency that ground-based vehicles can only dream of. This is not a distant reality, but a future that's being shaped as we speak. But how do we make this leap from the ground to the sky? How do we ensure safety, efficiency, and seamless integration with existing transportation systems? The answer lies in the realm of quantum physics, in an equation that's as groundbreaking as it is complex: the McGinty Equation, or MEQ. The MEQ is the brainchild of pioneering minds, a mathematical model that integrates quantum field theory and fractal mechanics. It's an equation that could hold the key to making urban air mobility a reality. The McGinty Equation is like the DNA of urban air mobility, an intricate code that needs to be understood, decoded, and mastered. In its simplest form, the MEQ is a blend of quantum field theory, fractal mechanics, and perturbative effects of gravity. It's a model that represents the dynamics of aerial vehicles in an urban environment, accounting for factors like gravity, friction, and the fractal nature of the urban landscape. But don't worry, we won't be delving into the depths of quantum physics just yet. For now, it's enough to understand that the MEQ is a vital component of the future of urban commuting, a key that could unlock the skies and transform cities as we know them. Understanding the McGinty Equation is key to grasping this future of urban commuting. So buckle up and prepare for takeoff as we journey into this exciting new frontier. Dive into the heart of the McGinty Equation. It might sound complex, but worry not, we'll break it down. The McGinty Equation, or MEQ, has three main components. First, there's the solution of the free quantum field theory, represented as PSQ of TXT. This is the part of the equation that deals with quantum mechanics, the study of particles at the smallest scales. It's like the foundation of a building, the base upon which everything else is built. Next, we have the fractal potential term, denoted as psfractal XT DMQS. Now, the word fractal might be a bit intimidating, but it's simply a pattern that repeats at different scales. Think of a snowflake or a fern leaf, where the whole has the same shape as its parts. In the context of the MEQ, this fractal term represents a self-similar structure in the quantum field. It's like the architectural design that gives the building its unique shape and character. Lastly, there's the perturbative effects of gravity, symbolized as sgravity, XTG. This part of the equation accounts for how gravity, the force that keeps us grounded, influences the quantum field. It's as though we're considering the effect of wind on our building, subtly shifting and swaying its structure. When we combine these three components, we get the full McGinty Equation, PSXXT, equal sign PSQFTXT, plus PS fractal XTDMEQS, plus PS gravity XTG. It's a bit like assembling a building from its foundation, design, and environmental influences. But of course, this is a simplified explanation. The actual math involves integral calculus, Laplace transforms, and the convolution theorem. It's a bit like the detailed blueprints, precise measurements, and meticulous planning that go into constructing a building. Now that we've demystified the McGinty Equation, let's see how it changes when we introduce modifications. Modifications to the McGinty Equation bring us closer to the reality of urban air mobility. The McGinty Equation, as we know it, is a complex mathematical formula, but let's break it down. It's essentially a solution of free quantum field theory, coupled with a fractal element. The fractal element represents mechanical systems and is described by a host of parameters. But the world we live in is not just quantum and mechanical. It's also gravitational. That's where the modified McGinty Equation comes in. It introduces an additional term, gravity, representing the perturbative effects of gravity on the quantum field. This parameter g is what characterizes the strength of the gravitational force. This modification doesn't just add a term to the equation, it brings the equation closer to real-world scenarios. It gives us an equation that is more applicable, more practical, and more powerful. It's like adding wings to a car. Suddenly it's not just a car anymore, it's a flying car. The fractal correction term can be derived using integral calculus, Laplace transform, and the convolution theorem. This self-similar fractal structure is described by constant parameters, adding a level of predictability and control. In the end, what we get is not just an equation, but a key that unlocks the door to a future where urban air mobility is not a dream, but a reality. With these modifications, the McGinty equation becomes a powerful tool for envisioning our urban air mobility future. So, how does the McGinty equation fit into the big picture of urban air mobility? An intriguing question indeed. The McGinty equation, or MEQ, is a complex mathematical formula that's more than just numbers and symbols. It's a key that could unlock the future of urban air mobility. You see, the MEQ essentially describes the behavior of quantum fields and the effects of gravity on them. Now, you might be wondering what quantum fields have to do with air mobility. Well, the principles underlying the MEQ offer profound insights into the dynamics of mechanical systems, which include our future air mobility systems. Imagine this: a city where aerial vehicles dart through the skies, efficiently and safely transporting people and goods. The design and operation of these vehicles could be significantly informed by the MEQ. Understanding the influence of gravitational forces on quantum fields, as described by the MEQ, can help us create more efficient, safer, and more reliable aerial transportation systems. Moreover, the fractal structure represented in the MEQ mirrors the complex, ever-changing urban environments. This resemblance could offer invaluable insights into navigating these environments effectively, enhancing the efficiency and safety of urban air mobility. As we stand on the cusp of this new era, the McGinty equation offers us a mathematical glimpse into the future of urban commuting.